So today we're going to be talking about binary trees, and afterwards we're going to be talking about binary search trees, a better way to use binary trees. So if you haven't seen my linked list video, technically, really a binary tree is really like a linked list, but instead there's like you can point to two ways. Okay, so let's compare. So before, a linked list looked like this, right? Head points to a node, and this node only points to one node, and this node only points to one node, and let's say this is the last node right here. Uh, then we'll just point to null pointer, right? Null pointer, right? That's what a linked list is. Basically, each node points to only one node, unless it's like a doubly linked list. Then we'll just point back to each other. But let's assume this is just a singly. Okay. So one node points to another node, and that node points to only one node. Notice how I'm saying only one node. Okay. That's given like a hint. Okay. So that's a linked list. That's not what we're talking about today. So today we're gonna be talking about I can move this. Wow. Okay. So today we're gonna be talking about a binary tree, if I can spell. So what a binary tree really is, it's legit just like a linked list, but instead it has like two next pointers, which are gonna be left and right. Okay. So let's make one real quick, like drawing wise. So let's make this, and then right here, these two nodes are gonna be pointing to another node, and then this node, and then let's say this one doesn't. Uh, like if it doesn't point to a node, what I see is you do this. So down this is left here. Let's put this left. That's a that's a left, and this one's right. So this node right now has a left and right pointer, right? It's pointing to something. This one has one to its left, but doesn't have one to its right, indicated by this symbol. We'll just like I'll just do a guide. Guide. This means a null pointer. Okay, so that means null pointer. Over here, let's just say this also we'll do one here. So this one's left is pointing to null pointer, and this one is then its right is pointing to an actual node. Same here, you know what? Why not? Let's do here. Okay, good. So let's go over this again. So actually, since you can see my cursor, so this one right now, right, has two children. One on its left and one on its right. Its left pointer is pointing to something, and its right pointer is pointing to something. Let's go to its left first. Its left, this node's, its left points to null pointer. So there's nothing to its left, but there's something to its right. Its right is pointing to another node, which its children is just like null pointer. So technically no children. Let's go back all the way to the right. So left and right. Left has a child. Right, null pointer. Let's go to the left child again. Null pointer, null pointer, as indicated by this symbol. Let's draw this better. Let's let's do that a little longer. This one is shorter. Okay, yeah. So how are we gonna do this? Okay, so let's just make a struct real quick, and let's like build this node. So let's call it a node again. Let's call node like BT for binary tree. So node binary tree. Now let's compare it with the node of like a linked list in case you don't see the difference yet, which hopefully you do by now, but it's okay if you don't. Okay, so struct over list. So for a struct for a linked list, technically it's just like today we're just gonna do like numbers. So in data, and then let's do what should we do? Node ll next. So pointer to the next node, right? And then we're just gonna have a simple constructor here, like data equals -1. Let's assume like you can't have negative numbers in this like in our data, right? So we're just gonna make it a -1, and then next equals null pointer, and then for like let's do it. We'll just do that for now. And then here, so you know how I said it's legit just like a linked list node, except it has two ways of going. Exactly. So right here we're gonna have int data, right? Because each node here's let's draw numbers. So one, two, three. over here, let's do one, two, three, four, five. Okay, so that's how it holds data. Okay, that's it. So let's go over here, node BT, and then we're gonna have left and we're gonna have right. Just to make it like more readable, I'm just gonna have another one, node BT right. Okay. So and this because we do have there, let's just make a constructor. BT, a default constructor, data equals zero, -1, left equals null pointer, right equals null pointer. Okay, good. So let's constructor. Okay, so you're probably wondering, okay, what's the difference between using a binary tree and a linked list? As right now, nothing. Okay, unless we use techniques to make it faster. Okay, that's where a binary search tree comes in. But for now, let's just uh let's just try and make this right here. Like this like node. So it's like 1, 2, 3, and then 4, 5. So we're just gonna make head. So we're gonna make node BT, right? Head equal a new node BT. My bad. Right? Just call default constructor. We don't even need this really, but like just to be nice about it, let's just do that. Then we're gonna say head data equals a 1. Okay. Just to make it better, how about we just delete that? So it's gonna say 1, 2, and 4. Just to make it better. Maybe later on it'll be better for the binary search tree. But for now, let's do 1, 2, 4. Okay. So head data equals 1. That's what we want. So over here, we want head left data equals 2, right? No. Okay, as of right now, we're just gonna draw what we have right now. Okay. Because this would all right, sorry for that little cut. Okay, let's draw what we got right now. Because this would technically like segfault. Because we're trying to access something that's pointing we're trying to access data that's pointing to null pointer, which is 0x0. And now the computer's like telling you like what are you trying to do? You're trying to get something, you're trying to make add 0x0 a 2. That doesn't make sense. So let's not do that. So let's draw what we got right now. We're trying to draw this. Okay. We're trying to get this. So this is let's do what we want. Okay, want, right? And what we got is right here. So what we got. Right now we got head points to this, right? Points to a node. And right now, because we made it by default on the default constructor, it's null pointer. Okay. So and then see that's like this line right here, right? Data is right now, as of right now, it's -1. Because by default constructor, it's just making -1. Left equals null pointer, right equals null pointer, right? Indicated by this, -1, boom. Okay. So head arrow data. So head arrow data, so we're talking about this right here, equals 1. Okay. Boom. Now the data inside equals 1. Nothing bad so far, right? So now we want to make the left and right node 2 and the 4. So right now, we want to allocate new data. Okay, allocate memory for the left child. So what we want to say is head left. So we're talking about this pointer right here equals new node BT. Okay, let's draw what we did right now so we can see everything that's happening. Boom, right? And as of right now, -1 constructor left equals null pointer. Okay, boom, boom. 488. I don't think this really matters, but let's just do that. I'll explain later, but I feel like that's just better. So what we're gonna do is new node BT, and then that's what we want, right? So far. Now we want to make this a 2, so we're gonna do this. Head, arrow, left. So what's left pointing to? Left is, let's put an arrow here, point to this. Now what do we want from that? Okay, arrow, because left arrow, data. Okay, equals. What do we want? 2. Okay, let's see what we got so far. Okay. So I'm gonna just put a cout empty. And I'm gonna run debugger just to see what's up. Just see if I got this right. Okay, that way, because I can't really see because I'm using the Windows quarter thing. So there you go. I'll just put a breakpoint. There you go. Okay. So I'm just gonna go actually to here, continue. Okay, it didn't crash. That's good. Okay, head, right. That's good, right? Because right as of right now is a null pointer. That's what it's doing right now. Left, data equals 2. That's good. And guess what? Left, this node apparently is left null pointer, right is null pointer. Boom, boom. It's going good. But what I forgot to draw was this right here, the 2. Boom. Good. Amazing. Perfectly hopefully good, right? So we're gonna go do the right now. So you probably have an idea of how to do the right now, hopefully. I really hope. So what we're gonna do is head right equals new node pt. Just put the parentheses because why not? Head right equal data equals what do we want it? 4. Boom. Right? Let's draw what we got. Kind of okay, let's go with this line, right? So this line, what we did, we made a point to something. That's good. We made a point to a node that we have. As right now, it's -1. And these are making it to null pointer. Okay. Indicated by, again, the constructor. Because data equals -1. That's what we did right there. Left, right, null pointer, null pointer. Okay. Head. Okay. Arrow. Right. Okay, we're talking about this right here. Arrow. Okay. Data equals 4. Okay. So all we gotta do. Okay. Well, not all we gotta do. It's just we just gotta draw 4 here. Okay. That's what we got so far. So let's run debugger again. Okay. Let me move this, and hopefully I can see it now. There it is. Okay. Okay. Head right now, right? That's good. It's pointing to something. Left and right, good. It's pointing to something as well. And guess what? Data equals 1. If I press left, it should have data. Its data to be 2. That's correct. Left and right, null pointer, null pointer. Okay, good. Right, left, right. Okay, null pointer, null pointer. And guess what? Its data is 4. Perfect. Good. Okay, that's what we needed. That's what we got. All right, perfect. Boom. So you're probably wondering now. I exited this program, right? And let's run Valorant on it. Let's see what happens if we run Valorant. Mhm. So I don't know why I did the slash edit out. Obviously, just into that, right? If we did the Valorant slash edit out, guess what? We have a leak. Not good at all. Oh wait, leak summary right here. Definitely lost 24 bytes in one block. Indirectly lost 48 bytes. Just to sum it up, all in total, we lost memory. Okay, there's a memory leak. So how do we like talked about like in let's go back to linked list, right? How do we deallocate a linked list? So how we did it, does it correlate? I don't think it really correlates. No, it doesn't really correlate. So before we get into like deallocating, we need to talk about how we traverse. Okay. So there's 3 things. Okay. There's 3 ways to traverse a binary tree. Okay. So there's pre-order, post-order, and then in you know what, just to make it nice. It's in pre-order, in order, post-order. Okay. So let me pause real quick and make a drawing. Okay, so we got this drawing right here, right? So don't worry about what we got because that example's gone now. Okay, so let's do pre-order first. So pre-order, the first, the immediately the moment you reach the node, you want to process that node. Okay, so for example, head, we always gotta start from head. Okay, so it goes 1. So the moment we're on the node, we have to process it. Okay, so all we're gonna do, let's say, for our definition of processing it, all we're gonna do is see out the data. Okay, so right now we're just gonna do as of right now, since we're here, right? I'm putting I. Is there a way to wonder if you can do this? Oh, we could. Okay, so I is right here, right? That's what we're viewing right now. So as right now, we have processed one. So we have C added one. Okay. So when we usually do binary trees, we always want to go left and then right. You go right and left, but for this example, let's do left and then go right. So we're gonna go left, right? Oh, immediately process it. Two, right? Okay. From here, we're gonna go left. Three. Boom. Okay, let's go through three. Okay. Uh, where is it? Okay. We try to go left, but guess what? It's null pointer, so don't go. Okay, now we go right. Guess what? It's null pointer. Okay. Now it's gonna recursively go back up. Okay. So we're gonna talk about the function later for like pre-order, in-order, post-order. For now, just know it will recursively go back up. Because we already look left, we're gonna go right now. Okay, five. So since we immediately saw it, we're gonna process it. Okay, five. Okay, okay. Left, no pointer. Right, no pointer. Come back to two. Since we already processed left and right, we're gonna recursively go back up. Okay. Hopefully you're getting the sort of thing now. Four. I'm not even gonna like talk about it because I already know you know it. Hopefully, just in case. Okay. Now we're gonna go left. Six. The moment you see it, we're gonna process it. There you go. Boom. Left. It's no pointer. Right. No pointer. We're back to the four. Recursively go back. Okay. Now we're gonna go right. Seven. Seven. Left. No. Right. No. Recursively go back. Since we already went checked left and we came from right, we're gonna go recursively go back. Since we already checked left and right, we're done. Because we came back to the head node, the original call, the original recursive call. Okay, so we processed this binary tree 1, 2, 3, 5, 4, 6, 7. Okay, and we're gonna label this pre-order. Okay, now let's do it in order. Okay, okay. So for in order, you have to process the left, and when you come back to your recursive call, then you'll process it. Okay, hopefully it will make sense. So right now, we can drag the I. Okay, have we processed left yet? No. So we gotta go left. Have we processed for this node? Have we processed the left side? No. Okay, now we go here. Okay, let's process the left side. Oh, it's no pointer. So now we process the three because we processed the left side for this node. Okay, now we go right. Oh, oh, no pointer. We can't go back. Now, since we're back at this node, did we process the left side of its node? Yes, because we came from three. So now we're gonna process the two. Now we're gonna now we're gonna go to the right side. Not process it, but we're gonna go to its right child over here. So now we're at five. Before we process the data inside that node, we gotta go left. Oh, it's no pointer. Now we process it. Let's go. Right, we can't. Okay, now we go back, recursively go back to two. Now we can recursively come back to the one. Did we look at one's left side? We did. Because we went through three, two, and five. So now we gotta process it. So just one. Okay. Now we're gonna go to its four. Did we process four's side? No, we didn't. Not four side. Four's left side? No, we didn't. So we're not gonna process it yet. So we're gonna go to its left side. Six. Did we process six's left side yet? No. So we're gonna go to left side. It's no pointer. Come back. Now we process it. Okay. Now we recursively go back to not yet actually. First we gotta go right to its right child. It's no pointer. Come back. Recursively come back. Now since we checked out its four's left side, now we can process the four. And now we go to its right child. Did we check out this one's left child yet? No. It's no pointer. Come back. Seven. Boom. Then check out its right child. Nothing. Nada. We already checked. We already processed it. Already processed it. Boom. So as you can see, this one's different because we visited the nodes in a very different way. As you can see, this was pre-order in order, so now we got different numbers, obviously, right? So last one is pre-order. Okay. Okay, let's do this. Okay. Let's make this bigger because I feel like it's gonna be bigger. So in pre-order, you have to process. It's not pre-order. What am I talking about? Post-order. So before you process the node, you have to go look at its left side and then its right side. Okay, until you process the data. So let me ask you a question, right? Figure this out real quick. Which number do you think it's gonna be the last number? Think about that real quick. Okay, so you're done thinking, hopefully. So now we're checking. Okay, did we process this left and right? No. So we're gonna go left first. Did we process this left and right? No. Did we process this left and right? No. No pointer, no pointer. Three. Okay. Kind of go faster because I feel like you hopefully get it. Three, right? So now we're gonna recursively come back. Did we process this left and right? No, because we haven't checked this right yet. So we're gonna go here. Did we process left and right? No pointer, no pointer. Now we did. So now it's five. And then now we come back here. Did we finally process this left and right side? Yes. So now we do data two. Now we're gonna come back though, right? Did we process this node's left and right? Think about that for a sec. Answer is no, we didn't. Because did we check out 4, 6, 7 yet? No, we didn't. So we're gonna go on to its right side, 4. Did we check out four's left and right side? No, we didn't. So we're gonna go on the left side first. 6. Did we process it? No, no pointer, no pointer. Okay, now we did. So now this is 6. So here, right? Just did we process four's right side yet? No, we didn't. So we're gonna go to the 7. No pointer, no pointer. 7. Now it's gonna go all the way back up. 4. Did we finally process the left and right side? We did. Thank God. So now we're here. 4. Okay. Now we're gonna recursively go back up. 1. Did we finally check out one's left and right side? We did. Okay. So last thing to be processed is 1. So I'm not gonna lie to you, it's not even that bad. The the way to how to say this, how to make the function for this is not even bad. It's gonna be 3 lines max. Actually, uh less than 10 lines for sure. Okay, less than 10 lines. Should be less than 10 lines. Okay, so what we got right now for like here, let's do void pre-order head, and then yeah, if I can do this quickly, that'd be nice. Okay, we have pre in post, right? Uh, I only have the 1, 2, and 4. Let me do 3, 5, 6, 7 real quick. Yeah, I think I did. But real quick, let me just debug. You know what I mean? Just in case. Let's go through this. Just in case. Okay, head is, 1. That makes sense. Let's go left side first. Left, it's 2. Okay, let's check out left. It's 3. That's good. Right, it's 5. Yeah, that's good. Let's check out the right side. It should be 4. 4. Left, 6. Okay, right. 7. Okay, good, 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 good. Okay. I'm telling you, easiest thing. Okay, it's just a recursive function. Okay, hold on. Matter of fact, uh, let me call these functions real quick. So it'll be nice. Hopefully in one try I could do this. Okay. Pre-order head, and then we'll do cout indo, right? Okay, this one's gonna be n. It's gonna be post. Okay. Boom, 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 boom. Pre-order. So moment we see it, right? We're gonna process it. So first we're gonna see out. Actually, no. First, okay. We always gotta check out what's our recursive case, right? So if current node we're on is null pointer, then we gotta stop. So if head equals null pointer, we'll just return. Okay, we're done. Just if I can spell right, return. Right. So in pre-order, the moment we see the node we're on, we're gonna process it. So first we're gonna say C out. If we're here, by the way, that means we're in a good node. So head data, right? And we're just gonna be nice about it, like kind of like how I process the other nodes. We're just gonna put a comma, and there's gonna be a comma without a number. It's fine. Okay, we don't gotta look nice. We just gotta care about how do we process these nodes. Okay, so C out head data, and then what do you think? How should we do the recursive calls now? Think about it real quick. Okay, so hopefully you thought about it. Pre-order, right? And then head left. Then pre-order head right. That's it. Let's try, just in case, let's try doing it real quick. Oh, I closed 1, 2. Okay. 1, 2. Okay. Hopefully, 1, 2, 3, 5, 4, 6, 7. Boom. We did it. Okay, good. Now, maybe hopefully you have an idea how to do the rest. Okay. It's just gonna be copy and paste. Sort of. Copy, right, paste, paste. All we're gonna do for in order, boom. For post order, done. That's it. That's how you navigate through binary trees in pre-order, in order, and post order. Okay, that's it. So hopefully when we do this, check it out. 1, 2, 3, 5. Oh, we already know that's right. Ooh, okay. 2, 3, 5, 1, 4, 6, 7. Let's check out that one. Hmm. Let's see how I did this in order. Okay, left, left, 3. Hmm. Wonder what I did wrong here. Hmm. 3, 2. Pause real quick. Okay, so I figured out the problem. It was legit just I copy and pasted it, so I didn't change the function call. So as you can see here, I changed the function call, and now it is working. Okay, good. See, wait, let's check out 3251647, 3251647, 3526741, 3526741. Okay, works, right? So, but what doesn't work is this. Let's try to do Valgrind again, obviously. And there's still bytes lost, even more bytes because we have more nodes, right? So how do we do it? How do we deallocate such a thing? Okay, think about it real quick. Okay, hint, it's gonna be one of the orders. Okay, instead of processing, it's gonna be deleting. Okay, so which one do you think it's gonna be? Okay, let's go top down because why not? Pre-order. So let's say we deleted it. Let's say we deleted the moment we process it, right? So for this one, we're gonna. So this one, right? We see it. Boom. We see the one right now. Okay, we're gonna delete it. Actually, just in case, I'm just gonna draw this. Okay. Okay. Now we're gonna go left. Delete. Left again. Delete. Oh, we're coming back. But we're coming back to memory that we already deleted. No can do. We cannot do that. No, no, no. We can't do that. Okay, next one. In order. Okay, maybe this could be the one, right? So this one we can't delete it because we haven't looked at the left side. Not left side. 3. Okay, delete. Okay. 2. Delete. 5. Delete. But guess what? I'm currently viewing deleted data. Now you might be wondering, okay, maybe that's not that bad. Actually, no. Don't mind what I said. Guess what? Guess what we did? We deleted, right? But then we try to access deleted data by looking to the right. Well, it's already deleted. So we can't do that. We cannot do that. What was I trying to say? We can't do that, right? So last option was it? Post order. Yeah. No, I saved the last one for because it was the answer. But hopefully you got it. It was post. So you can't delete this, you look till you look at your left and right. Okay. Can't delete this, you look at the left and right. Can't delete this, you look like left and right. base case is that if it's null pointer, come back. So this one, since null pointer, delete, right? We come back, go here, delete, null pointer, delete, null pointer. Oh, since we came back, actually not null pointer, since we came back from our deleted data, we already know, we know for sure that left and right is deleted, so we know this deleted. So we go back here. We can't delete one yet because it's a post order. Okay, so go here 4. We didn't go left or right yet. Left and right again. 6. Null pointer come back. Null pointer come back. 6. Deleted. Okay, now we go here 4. Can't delete yet because guess what? We haven't seen yet. 7. 7. Null pointer. Null pointer. Deleted. Come over here 4. Since we came back from recursive call from the right side, we know for sure that we saw left and right. So delete. Come back here. Since we saw left and right, deleted. Boom. We'll just make a function like void deallocate. What am I trying to head? There you go. If head equals null pointer, then return exact same thing, right? Except we're gonna do deallocate head left, deallocate head right, and then what we're gonna do here? Delete head. Delete what we're currently viewing because we know for sure that is deleted. So let's see. Let's see what's gonna happen when we try to do deallocate and head. Let's see what happens. Let me do, oh, not that. G++, let's compile it first, and then let's see if it's still running. It still runs. So now let's do Valgrind. Yes, no leaks are possible, because guess what? We did post order, and then boom. Okay, so I think this is enough for this video. This video is already too long. It's like 30 minutes. Who wants to go through 30 minutes of C++, right? So I'm just going to leave it off here. Binary search trees is the next video, hopefully. And yeah, hopefully you understood. Have any questions, put in the comments, please. And then, yeah. So I'm just going to do this at the end of every video. Just like to see like a quick, because we just did, like, think about it. We just did 30 minutes of C++ coding and talking about a new topic, a new data structure. It's not that fun, right? So this is more fun. We're just gonna talk about what did we learn today, right? What's something new that we learned? So what the new thing we learned was that we can. It's a it's basically the best way to think about it. It's a linked list, but instead there's two ways of points for each node. So each node in a linked list normally, basically only points to one, right? Only one node, and that node can only point to one, unless it's a duplicate. If we're talking about a singly linked list, only one, right? It's only one pointer. But in a duplicate, it points to its front and back. This situation, each node points to two nodes. So in this case, left child and right child, right? And as right now, you're probably wondering, okay, what's the point of using a binary tree? That's not until we learn about binary search trees, which should be in the next video. Let's get these dudes real quick. Okay, so and then what else did we learn? Ways to traverse binary tree. We learned about pre-order, in order, post order, and that's pretty much it for now. We're gonna learn about nothing. Another one is called what's that called? Level order, which uses something called a queue, which I made a video on as well. If you want to look at that, and then what else? Yeah, so we learned of ways to traverse it. Okay, as I was going off, what's the point of using a binary tree if I can just use a like a linked list, a vector? Well, what's cool things is the binary search tree, AVL trees, red black trees. I heard. Uh, Binary search trees just make it easier to look at data. Because as of right now, when we're going through that binary tree with like post order, in order, pre order, we didn't really have rules, right? So the data we like were going through, it wasn't sorted. It wasn't there wasn't really like any correlation between the data. With a binary search tree, And AVL trees and all the other type of trees, right? There's rules to how you put data into the tree. With a binary search tree, I'll just give you a quick like glimpse into it. Whatever's left of the node is less than the current data. So let's say like head is, imagine this real quick. Head is like 1. So anything less than 1 will go to the left of it. Anything greater than 1 is going to go to the right of it. So left child, let's say it could be -2. Right child could be negative, no, not negative, but like 1500. No, something bigger than 1. Now let's go to the 1500, right? Anything less than 1500 will go on the left side of it. Anything greater than 1500 will go on the right side. That's basically like a quick review of what binary search tree is, right? I think that's pretty much it.